Hello and welcome to the third online summer school for the assumptions of physics. Today we are going to talk about reverse physics. Tomorrow we are going to talk about, we'll give an introduction and results in physical mathematics. And the third day we are going to talk about open problems. This year we decided to break it up a little bit, so I'm not going to be the one that gives all the lectures. The first day is going to be Professor Cristina Idala. The second day is going to be Tobias Trien, our student, and I will be talking about the open problems. And the idea is that we're trying to sort of build a community around the research program. So ideally, maybe in a few years, there's going to be other members of the community that starts taking some pieces, and then we can even talk about, people can then present the results of their research contribution. For how it will work, we're gonna take questions within Zoom. People can write the question whenever they want, and they can upvote questions of other people, so that we try to maximize the questions that are of more general interest. And if there are short clarificatory question, I will interrupt the speaker and either give the answer myself or ask the speaker to give the question. So I think that all covers it. So we'll jump in right away. Professor Cristina Dalla, take it away.
All right. Yes, I'll be getting us started with an introduction to reverse physics. But first, let me step back and briefly talk about the broader assumptions of physics research program that Gabriel and I co-founded. So the main goal of the assumptions of physics program is to identify a handful of physical starting points from which the basic laws of physics can be rigorously re-derived. For example, if I have a ball, I can study the motion of the ball as a whole, or I can take a red marker, make a dot on the ball, and study the motion of the red dot. So in classical mechanics, studying the motion of the ball as a whole or the motion of all the possible infinitesimal red dots I can make is going to be equivalent. I can instead, if I have an electron, I have the opposite case where I can study the dynamics of the electron as a whole. I can't take a red marker and make a dot on the upper left back part of the electron and study what happens to that. And so I have I can know nothing about the state of any internal dynamics parts of my quantum state. We'll talk more about these later. And so this program also requires rederiving all mathematical structures from physical requirements. For example, starting from the very foundational notion that science is evidence-based implies that any scientific theory must be characterized by experimentally verifiable statements. And you'll see in Tobias's lectures tomorrow how this leads to topologies and sigma algebras as the foundational mathematical structures upon which all the mathematical structures used across all physical theories are built. So the standard view of the foundations of physics is that the goal of physics is to find the true laws of the universe, and this is the real physics. So the foundations of physics are the theory of everything that we are trying to find, and then everything else is an approximation. Our view instead is that, well, we found that physical requirements and physical assumptions drive most of the theoretical apparatus used across physical theories. For example, we found, as I already mentioned, that experimental verifiability leads to topologies and sigma algebras. We found that geometric structures are equivalent to entropic structures in physical theories. Hamiltonian evolution is equivalent to assuming deterministic and reversible evolution plus degree of freedom independence. We'll talk more about that later. And massive particles and potential forces come out from assuming deterministic and reversible evolution, degree of freedom independence, plus an assumption we call kinematic equivalence, that there's an invertible map between conjugate momentum and velocity. So our view is that the goal of physics is to find models that can be empirically tested. We don't claim that this is the only possible view of what the goal of physics is, but we feel that it's a very productive point of view. We've really been able to get a lot of insights from this starting point. So our view of the foundations of physics is that the foundations of physics is the theory of physical models. So it's the theory of all possible physical theories. So at the very foundation, we have general physical principles and requirements that would apply to any physical theory, all the current ones, any ones we might find in the future. From these most general physical principles and requirements, we develop a necessary general mathematical framework. And then on top of that, we can make a variety of different specific assumptions that lead specific physical assumptions that lead to the different theories within physics, such as classical mechanics, quantum mechanics, thermodynamics, etc. So within the Assumptions of Physics program, we have two approaches, a top-down approach that we call reverse physics and a bottom-up approach that we call physical mathematics. Today is focused on reverse physics. So reverse physics, we take inspiration from reverse mathematics, which was founded in the 1970s, where people working in reverse mathematics start from an established mathematical theorem and try to identify the smallest set of axioms required to prove that theorem. For reverse physics, we're starting from an established physical theory, reverse engineering things to try to identify the smallest set of physical assumptions required to rederive that theory. So the goal of reverse physics is to find the right overall physical concepts. We want to elevate the discussion to focus not on the mathematical constructs of the theories, but to focus on the physical principles that are implicit within those constructs. Physical mathematics, instead, our bottom-up approach. We're starting from scratch and rederiving all mathematical structures from physical requirements. The goal of physical mathematics is to get the mathematical details right and to end up with a perfect one-to-one map between mathematical and physical objects. So moving to focus on reverse physics, the topic of today. When the math is derived from the right physical assumptions, the physical assumptions can be derived from the math. So reverse physics aims to adopt approaches that are more in line with the foundations of mathematics, breaking physics into a set of physical and mathematical conditions with well-understood logical relationships among them. It's really a new methodology for the foundations of physics. So what are the goals of reverse physics? Well, we want to be framework or interpretation or formulation and theory neutral. We want to allow for each result to be independently formulated from other results. In reverse physics, we want to uncover paradoxes or contradictions that are in our existing theories or in the mathematical structures of our existing theories and develop standards of rigor appropriate for physics. We want to clarify the logical dependencies of various physical and mathematical conditions within our theories, and we want to identify core constitutive requirements of all physical theories, which we call the Big Four of reverse physics in reference to what's known as the Big Five in the reverse mathematics program. And we'll get to that later in the lecture. So just a note, we're relevant throughout today's lectures. I've given the links to our published papers as well as what we call technical briefs, which are relatively short documents that are available on our website that really just have the technical content without the full development that you'd have for a published journal article with the introduction and citing various literature. So they just focus on the specific results, the technical briefs. And you can find more details from the links. So one of the main things we do in reverse physics is to examine the actual physical content of the mathematical structures that we use for different theories within physics. So for example, if I want to apply reverse physics to Hamiltonian mechanics, then my classical state, is going to be a point in phase space. I have the Liouville measure, which provides a count of states. You can also view it as the integral of the symplectic form. In Hamiltonian mechanics, I'm assuming Hamiltonian mechanics, so I start with Hamilton's equations. So these are mathematical expressions. Well, what are different ways of looking at them? What do they actually mean? So a different mathematical way of looking at them is that they are a symplectomorphism, so that the symplectic form doesn't change in time. Well, if the symplectic form doesn't change in time, we said that the integral of the symplectic form represents the count of states, the Liouville measure. So the Liouville measure is not changing in time, and this means we have conservation of state count. And this is already a more physical notion. If I have conservation of state count, that means I have a one-to-one map between states at time t and future states or past states, and with state count conserved as a function of time. So this leads us to the physical notion of deterministic and reversible evolution. So deterministic and reversible evolution of classical states is equivalent to Hamiltonian mechanics, is equivalent to all the pieces listed here, including Hamilton's equations. Yeah, so if I have deterministic and reversible evolution, I'm also going to have conservation of thermodynamic entropy. So I have conservation of the log of the count of states as the entropy. You can see we have equivalences there. We're also going to have conservation of information entropy. So I get and conservation of uncertainty as well. So we get this whole suite of different equivalent conditions, some mathematically framed, some physically framed, that give us a lot of different angles of looking at whatever theory we are examining with reverse physics and trying to tease out what exactly are the physical assumptions that are embedded in the mathematical structures used in a particular theory. As another example, I can do this with the Schrödinger equation in quantum mechanics. So now my state is a ray in Hilbert space or in the projective space. And the probability of state psi given state phi is given by the square of the inner product. And I take the Schrödinger equation. Again, I have this mathematical expression. What are different ways of looking at it? What are different physical and mathematical ways of looking at it? Well, I can think of this as unitary evolution in time. If I have unitary evolution in time, then I am going to have probability conserved in time. So the probability of psi given phi at time t is going to be the same as the probability of psi given phi at some future time t plus delta t. So I have a bijective map of state and probability. If I have this bijective map of state and probabilities between states, this again leads me to deterministic and reversible evolution. So deterministic and reversible evolution is equivalent of a quantum state is equivalent to the Schrödinger equation. We can link this to conservation of information entropy again, and again find a suite of different equivalent relations now in the context of quantum mechanics. And we see that the core physical assumption, but operating now in quantum states or as applied to quantum states rather than classical states, is deterministic and reversible evolution. So for the Schrödinger, equivalent to the Schrödinger equation in the case of quantum mechanics and equivalent to Hamilton's equations in the case of classical mechanics. So again, another example of using reverse physics to try to understand the physical content of the mathematical structures we use in different theories. We can apply reverse physics approaches to the principle of stationary action in classical mechanics. So we're going to be working in phase space extended by time. So QP, and now I have my time axis explicitly written out here. And the lines you see here are evolutions of a state, so a state in phase space evolving in time. And I can write this as a vector field. And an actual evolution is going to be tangent to a field line. We'll talk about this a lot in the second lecture and go through the details of recovering this. But in the end, we find that the action is the line integral of the vector potential of this vector field describing the flow of states. Since it's a vector potential, the action itself is going to be unphysical. However, the variation of the action measures the actual flow of states, and this is going to be physical, setting the variation, requiring the variation to be zero, so that you have stationary action, minimize the action, implies that the flow of states is tangent to the path so that you're going along an actual evolution. Again, we'll see this in more detail in the second lecture. Still using reverse physics to try to understand the physical content of the mathematical structures used in our theories. We can ask, what about phase space itself? What are the physical assumptions that lead us to require the mathematical structure of phase space, the symplectic structure of phase space? Well, if you think of a uniform distribution, so my flat distribution here, I can do a coordinate transformation, just relabel my coordinates. For example, take x, remap it to x cubed. Nothing says I can't do that. If I do that though, then what I what looked like a uniform distribution expressed in one coordinate system is not going to be a uniform distribution expressed in another. Similarly, what doesn't look like a uniform distribution expressed in one coordinate system, you can do a coordinate transformation and make it look uniform in another coordinate system. So in general, densities, entropies, and uniform distributions are not coordinate invariant. So how can we fix this? Well, for each unit variable, i.e. coordinate, if we pair it with the conjugate variable of inverse units, so if I have my q's that I express in meters, and I have my k's that I express in inverse meters, then if I have the number of states as the area in my pair of conjugate variables, so delta Q, delta K, this is going to be invariant. So if I do a coordinate change to now use centimeters instead of meters, I change my unit variable. I have to correspondingly change my conjugate variable. Here we'd have inverse centimeters, and so the product delta Q, delta K in the new coordinates remains invariant. So the phase space structure, the symplectic structure, is the only one that supports coordinate invariant densities, entropies, and state counts. This is really why we use phase space, so that we have these invariant quantities. So the invariance of entropy, the invariance of state count, plus degree of freedom independence. I just showed things for 1 degree of freedom here. They are equivalent to the structure of phase space conjugate pairs. And again, like I showed for Hamiltonian mechanics and the Schrodinger equation, we want to find many different equivalent conditions, some in more mathematical terms, some in more physical terms, that just give us a lot of different angles to view a particular idea or object with. So phase space in this case. How about the relationship between geometry and entropy in physical theories? Again, we're still thinking about trying to understand what physical content is implicit in the mathematical structures we use in different theories. Well, in classical mechanics, we talked about the count of states, and then the log of the count of states being is the entropy. Well, it's the symplectic form, which describes the geometric structure of classical mechanics. The symplectic form determines and is determined by the entropy of all uniform joint and marginal distributions, marginal across the different degrees of freedom. And if I, in fact, express the symplectic form in position velocity coordinates rather than position and conjugate momentum, I get the metric tensor appearing as the position velocity, the off-diagonal part of this symplectic form. So again, we have this equivalence between the geometric structure, the symplectic structure of classical mechanics, and the entropic structure of classical mechanics. How about quantum mechanics? In quantum mechanics, write our entropy of all equal mixtures of pairs of pure states, so 1/2 psi, 1/2 phi. And we have our entropy here. You can see our Born rule appearing. So the Born rule determines and is determined by the entropy of all equal mixtures of pairs of pure states. So again, we have this equivalence between geometric structures encoded represented by the Born rule and the entropic structures. Looking at the uncertainty principle, and where does this come from? So if we, I showed you before, back on a few slides ago, I wrote S of rho, the entropy, as minus the integral of rho log rho dq dp. I'm in classical phase space. You'll often see this written in textbooks, in fact, as just rho log rho dq dp, but it's actually dimensionally incorrect. So if you have a distribution in phase space, it has units of inverse phase space. So you're going to need some kind of constant here with units of phase space area, phase space volume. In order to take the log of a dimensionless quantity, right? You can actually take the logarithm of a dimensionful quantity. So we choose this constant to be 8. We write it as h. This is going to represent the the area in phase space, so a uniform distribution over phase space of this area H is going to have zero entropy. So my a uniform distribution of over phase space of area H would be rho equals 1 over H. So H times 1 over H equals 1. The logarithm of 1 is 0. So we get 0 entropy for a uniform distribution over phase space with the area of our constant. And we fixed the units so that we're not taking the log of a dimensionful quantity. So now in general, the Gaussian distribution maximizes entropy for a given uncertainty. So if I take as my distribution a Gaussian, and it maximizes entropy. So for any other distribution, the entropy would have to be less than or equal to the log of 2 pi e times sigma q, sigma p. So our uncertainty, if you're thinking of Gaussians, these would be the standard deviations divided by my constant that fixed the units and set the zero entropy area in phase space. And this would be equal when I'm dealing with a Gaussian distribution. So I can rearrange this algebraically and take the exponential of both sides and say that sigma q, sigma p must always be greater than or equal to h over 2 pi e to the e to the entropy. And I can write my h over 2 pi as h bar. So then sigma q, sigma p must be always greater than or equal to h bar over e times the exponential of the entropy. So it's entropy that's putting a lower bound on the uncertainty. And so this is actually the only feature of quantum mechanics that leads to the uncertainty principle in quantum mechanics. You don't need any of the rest of quantum mechanics. All you need to get an uncertainty principle is a lower bound on the uncertainty. Thermodynamics already puts a lower bound on entropy. In the third law of thermodynamics says that entropy must be greater than or equal to 0. So if we put an e to the 0 here, then we have sigma q, sigma p must be greater than or equal to h bar over e. And this is what we call the classical uncertainty principle. We'll talk a bit more about things related to this later on. Again, what is the physics contained in the mathematical structures that we use in our theories? So if there's this link between entropy and uncertainty, this gives us a link between classical mechanics and quantum mechanics. So one of our recent papers, we recovered classical mechanics as the high entropy limit of quantum mechanics. There'll be more on this in the second lecture. So here I have entropy versus uncertainty in units of h bar. And the blue line is the classical curve that I just showed you from the previous slide. So it's crossing at h bar over e. There's the red dashed curve across is the one for quantum mechanics that crosses at h bar over 2. And you can see how they coincide at larger entropies. And so recovering the classical limit, classical mechanics is the high entropy limit of quantum mechanics. What you're doing physically is increasing the entropy of mixed states. So if you think of your commutator, commutator between x and p equals I h bar, you're doing a stretching map such that you're rescaling things and you get the scale factor times I h bar. You're increasing the entropy of mixed states. This is equivalent to the mathematical limit that you typically see in textbooks. In textbooks, people often take the classical limit or recover classical mechanics by taking the limit as h bar goes to 0, which is, of course, unphysical, right? H bar is a constant. It doesn't go anywhere. So this would be analogous to taking c to infinity in classical mechanics to recover Newtonian mechanics from special relativity. So here again, you see entropy as a function of the uncertainty. It's written with a different symbol here, sigma q, sigma p over in units of h bar. Here's classical mechanics crossing 0 at 1 over e, quantum mechanics crossing 0 at so h bar over e, h bar over 2. And then we have the scale factor. We can instead rescale things differently. Start with the different coordinates and effectively decrease the entropy of pure states such that in the limit of the scaling variable, we take the limit of the pure state entropy to minus infinity, and we recover this classical curve that goes off to minus infinity. Again, we'll have more about this in the next lecture, but we think it's much more satisfying and sensible and intuitive to look at the physical limit rather than the mathematical limit. So in special relativity, in fact, taking and teaching courses on this, we talk about the limit of v over c much less than 1. We don't, in my physics classes at least, teach it as taking the limit as c goes to infinity. This c is whatever it is, and so the physical intuition is that you recover classical mechanics from relativistic mechanics in the low speed limit, and in quantum mechanics, we should think of recovering the classical limit by going to high entropy. Still thinking about the actual physical content of the mathematics we use in our different established theories. Sometimes you see arguments, you see physical people arguing that there are physical implications for the fact that we use linear representations in quantum mechanics. But again, applying the reverse physics approach to this idea, we can examine this, whether is there physics contained in the fact that we typically use linear representations in quantum mechanics. Well, we can come up with a map that introduces a total phase based on all the coefficients. So this is a nonlinear map. And that still preserves the physics, i.e. the Born rule. So we have a nonlinear map, a nonlinear representation that preserves all the physics. So therefore, we have to conclude that linearity is not a physical necessity. It's a mathematical convenience, and that's why it's typically used in quantum mechanics, but it's not actually containing physics itself. People also, there are also a lot of discussions of the physics implied by superposition in quantum mechanics. Writing a quantum state as a superposition of other states is really a property of the vector space representation of states in quantum mechanics. So this is mathematical rather than physical. What it physically corresponds to is whether or not your preparations are distinguishable. So any mixed state in quantum mechanics is multi-decomposable. So I can decompose a mixed state in quantum mechanics in terms of a sum of pure states in multiple different ways. So if you think of a spin 1/2 particle, I can represent the maximally mixed state as an equal mixture of z up and z down to get the center of the block ball, or I can equivalently represent it as an equal mixture of x left and x right states to again represent the same mixed state at the center of the block ball. And so this is this multi-decomposition, the fact that you can express a mixed state as a decomposition of different combinations of pure states, and that those preparations are not going to be distinguishable. So the indistinguishability of different mixtures is equivalent to saying that no physical process can depend on them. And that's what superposition is really about. This is what is key to quantum mechanics, making it different, or a key aspect of quantum mechanics that makes it different from classical mechanics. So that whole section was about trying to uncover the physical content of the mathematical structures used in our theories, moving to a sort of different aspect of reverse physics. Reverse physics also seeks to illuminate paradoxes or contradictions and to develop standards of rigor appropriate for physics. So some examples of this I already mentioned. You'll often see a definition of Gibbs entropy in textbooks as minus the integral of rho log rho, dq dp. But a density in phase space is not a pure number. So you can't actually do this mathematically. Take the logarithm of inverse phase space volumes. So you're going to need some dimensionful constant with a phase space volume, the appropriate number of degrees of freedom to correct this. Also, statistical mechanics, there are a lot of large n approximations. So here's a an expression taken from a derivation of the Sacher-Tetrode equation for the entropy of a monatomic ideal gas. For large n, they take 3n minus 1 and approximate it as 3n, but in this case, it's the exponent of a dimensionful quantity. And you can't approximate physical dimensions. So length, a length to the nth power is never approximately equal to a length to the n minus 1 power, even for large n. So these are the kinds of things that we want to uncover and bring to explicit attention in reverse physics and try to find ways to fix things, do things properly. We also have a paper from last year that discusses issues or contradictions that you can create doing quantum mechanics in Hilbert spaces. So for example, you can take a distribution or a state, I should say, that has a well-defined expectation value in some original coordinate system. You can do a coordinate transformation such that you end up having an infinite expectation of that. So basically different observers using different coordinate systems one will see a finite expectation for a quantity, one will see an infinite expectation for the same quantity. This is clearly unphysical. We can't have, it just doesn't make sense that for some physical observable, two people see, one sees a finite expectation for something and one sees an infinite. You can also do have your expectation values oscillate between finite and infinite in infinite time. Again, this is unphysical. So the underlying issue here is that every continuous linear operator defined on the whole Hilbert space is bounded. So this is a mathematical property of Hilbert spaces, and therefore unbounded quantities in physics that we need to work with, like position, momentum, energy, and number of particles, which never actually get to infinity, but they can be arbitrarily large, so they're not bounded quantities. These quantities are not defined on the whole Hilbert space. And so we can do these unphysical things. Hilbert space allows us to do unphysical things, and we want to bring this to light and try to find different spaces, different structures, so that we can avoid these problems, that we get a one-to-one, ultimately a one-to-one map between our mathematical objects and the physical objects they represent. You can also, this one we have a technical brief on, have inconsistent convergence in Hilbert spaces. So if you consider the sequence of quantum states given by this, so for I going from 1 to infinity, you just have a ground state with the coefficient out front, and then the ith state summed together. So you can look at this expectation value here and see that it'll converge to the first level, the first energy level. However, the sequence itself, the state, converges to the ground state. So this doesn't make sense. If I take if the state itself, the sequence of states, converges to the ground state, it's in contradiction with the idea that the sequence of expectation values converges to the first level. So again, these are things that Hilbert spaces allow you to do that are unphysical, and we want to find better mathematical structures that will avoid these issues. Also inconsistent units in quantum observables. So if you think of just the expectation of x, so I have psi x psi, should have units of x. But then, of course, x times psi cannot have the same units of psi itself. And typically, textbooks and discussions discuss x psi as if it's a map within the same space. But you can't be in the same space, given that the space of states itself does not have the same dimensions as the space of the observable operator times the states. So another mathematical issue that isn't typically treated well in textbooks. So that was about uncovering paradoxes and contradictions in the mathematical structures, the mathematical formulations that we use in our physical theories. moving on to another aspect of reverse physics. Reverse physics also seeks to identify logical dependencies and to develop and clarify base theories. So I already talked about classical mechanics a bit, and we'll talk about it more in the second lecture. But core assumptions in classical mechanics are infinitesimal reducibility. The classical state is infinitesimally reducible. We have independent degrees of freedom. These are assumptions across all of classical mechanics. In addition, I may choose to assume what we call weak or full kinematic equivalence. Weak kinematic equivalence says that there's an invertible map between conjugate momentum and velocities. Full kinematic equivalence says that the map between conjugate momentum and velocity is not only invertible, but it's also linear. And then determinism and reversibility, that can be an additional assumption, not necessary, that we talked about earlier. And then our different physical theories, where we have classical states in general, and then we have Newtonian, Hamiltonian, and Lagrangian mechanics, and massive particles under potential forces. And so we want to look at the relationships among all the different physical theories within classical mechanics. So again, we can make diagrams like this that help to understand the relationships among the physical assumptions and the different physical theories. So here I have infinitesimal reducibility, independence of degrees of freedom, lead us to classical states. So all of classical mechanics satisfies these two physical assumptions. And then if I have classical states plus determinism and reversibility, then I get Hamiltonian mechanics. If I have classical states plus weak kinematic equivalence, that I have this invertible map between conjugate momentum and velocity, I get Newtonian mechanics. Newtonian mechanics plus Hamiltonian mechanics gives you Lagrangian mechanics. And if I instead have not only this weak kinematic equivalence, but my invertible map between conjugate momentum and velocity is also linear, then I recover massive particles under potential forces. So we can see much more clearly the relationships among all these different theories within classical mechanics and the implicit physical assumptions that are made in the different theories. So a lot of classical mechanics textbooks actually say that Newtonian, Hamiltonian, Lagrangian mechanics are equivalent. I just have a blanket sentence like that. Although interestingly, then if you ask most physicists, even if that's what their textbook told them, about when you would use, I mean, in problems with friction, they're not going to use Hamiltonian mechanics. They would immediately heuristically recognize they should be using Newtonian mechanics, most likely as the easiest way to approach many problems with friction, for example, but they don't, they and many textbook writers don't have clear in their minds these relationships among the different theories. So in reverse physics, we want to make this all very clear and very explicit. And again, similar to what I showed before, each assumption is actually an equivalence class of multiple conditions, many different ways of looking at the same assumption in mathematical terms or physical terms. And this gives us many different angles from which to view a problem and really just gives a much greater insight, a broader picture of what's really going on in any given theory. So the goal of reverse physics, or a goal of reverse physics, is to create a base theory for all of physics, a collection of conditions that must be true in all physical theories. So additional different conditions or assumptions will then lead to different physical theories. So you make one set of assumptions like determinism, like classical states and determinism and reversibility. You get Hamiltonian particle mechanics. You can make different assumptions and get non-relativistic quantum mechanics, etc. But these will all be built on top of the collection. These will be additional assumptions on top of the ones that must be true in all physical theories. And then any new yet undiscovered physical theory must still be built on the base theory, the collection of conditions that must be true in all physical theories. And the base theory is not what people talk about as the theory of everything. So getting to the big four of reverse physics, so core constitutive requirements of any physical theory. We've identified these as experimental verifiability, reproducibility and ensembles, ensemble variability, and equilibria. So I can say a few words about each of these. And Tobias will talk a lot more about this one tomorrow when he covers physical mathematics. So we start from the notion that science is evidence-based. This differentiates it from pure mathematics, and therefore statements are associated to experimental tests in principle, whether or not you have technology or ideas about how to do this. But a verifiable statement, if true, your test will succeed in finite time. If a verifiable statement is false, it'll either fail in finite time or not return and be undefined. So you get this three-valued logic structure. And we'll see, I won't go into detail here, but that the verifiable statements will correspond mathematically to open sets. And as Tobias will show you, experimental verifiability ultimately leads to topologies and sigma algebras. And all experimental relationships must be topologically continuous. Moving on to reproducibility and ensembles, and parts of this work have been funded by the John Templeton Foundation. So here we're starting from the fundamental idea that scientific laws describe reproducible relationships. So if I have reproducible relationships in science, this leads to the notion of ensembles. And ensembles are outputs of repeatable processes. So I can have a preparation, a process that preparation process 1 that leads to ensemble 1, preparation 2 leads to ensemble 2, and I can do statistical mixing of two ensembles, and then I'll get another ensemble. And this statistical mixing of ensembles is what leads to linear structures in physics. So this physical concept is leading to this mathematical concept in any physical theory. Any ensemble, you can discuss the variability of your ensemble. So the variability of the elements within an ensemble leads to entropy. And if I have mutually exclusive ensembles, here you can see ensemble 1, ensemble 2. These are just sets of shapes. So ensemble 1 consists of a bunch of circles and just 2 stars. Ensemble 2, this distribution of shapes consists of a more balanced mixture between squares and triangles. The shapes in these are mutually exclusive, so there are no circles or stars in ensemble 2. There are no squares or triangles in ensemble 1. So these are mutually exclusive ensembles. Mutually exclusive ensembles are equivalent to orthogonal ensembles. And when you do a statistical mixture of orthogonal ensembles in any physical theory, you're going to have maximal variability increase. And the variability of ensembles leads to probabilities, inner products, and geometries. So probability is equivalent to mixtures of mutually exclusive ensembles. Classical mechanics, in classical mechanics and classical probability, this is equivalent to saying all pure states are mutually exclusive. And this is not going to be the case in quantum mechanics, right? So I can write z spin up, and that can be expressed as a mixture of x spin left and spin right, for example. So pure states are not mutually exclusive in quantum mechanics, but they are in classical mechanics. And then pure states are equivalent to the best possible preparations in any given theory. In the case of classical mechanics, so we can go to minus infinite entropy and have zero variability in the pure states in our theory, which is ultimately going to be unphysical, but that's how classical mechanics is mathematically constructed. That's an assumption that's implicit in the theory itself. In quantum mechanics, the zero lower bound on entropy is built into the mathematics that we use for quantum mechanics. And so the pure states, which are still the best preparations in quantum mechanics, they don't have minus infinite entropy. So it's not that they have no variability. So the best preparation is not equivalent to saying that there's no variability in your pure state. Equilibria is our fourth pillar. And this is the least developed part for us, something we still have significantly more work to do on. But this is the notion that states must, to do science, to define a physical state, the state must exist for at least some short period of time. So this gives us some general notion of equilibria. So it could be equilibria of internal processes happening at faster scales that don't matter, that we're not sensitive to. Or it could be equilibria of system environment interactions that don't matter, that we're not sensitive to. And that this requirement allows us to properly talk about different physical objects, one object distinct from another. And yeah, again, this is the least developed part, but equilibria should lead us to symmetries, differentiable structures, and Lie algebras in our base theory. So wrapping it up, assumptions of physics is a different approach to the foundations of physics, the research program as a whole, assumptions of physics. We don't have any interpretations. We're not trying to build a theory of everything or the theory of everything, as people tend to call it. We are using physically meaningful starting points from which we can rederive the laws of physics and the mathematical frameworks that they need. And we view physical theories as models, and we need to clarify exactly what the realm of applicability of each model is. Reverse physics within assumptions of physics, that's our top-down approach within assumptions of physics. We're reverse engineering physical principles from the known laws of physics in different theories. Now, the current laws in most physical theories are given through mathematical structures. They're really stated in mathematical terms, which often make it hard to understand the physics in them. There's really a very mathematical focus in, especially in more modern theories. And we have to find physical principles and assumptions from which to rederive the laws. These starting points must have a clear intuitive meaning for the majority of physicists and engineers. So in reverse physics, we want to identify physical principles and assumptions that make sense, that feel natural and intuitive to physicists and engineers. And reverse physics, we're investigating physics as a whole. We're not taking one theory as more fundamental than others. We really want to find all the interrelationships between and among the different theories that we have, the different mathematical structures that are used within them. So just to sum it up, reverse physics gives us a powerful new methodology for the foundations of physics, more in line with foundational approaches of other disciplines, offering a lot more and more precise insights and opening new avenues of research. So a few words about assumptions of physics. We conduct assumptions of physics as a completely open research program. Our main output is an open access book, which you can download either the published version or the latest working draft from our website for free. All our material is developed on GitHub, so you can see the whole repository there. Gabriel has one YouTube channel dedicated to publicizing results and another YouTube channel dedicated to the research, and he holds live stream discussions on that. This is the channel where we're streaming now. Activities are coordinated through a Discord server. You can contact info@assumptionsoffphysics.org for an invitation if you're interested. And for the Assumptions of Physics program, we're always looking for experts to gain insights and or provide help in different ways. So it's a very broad program, as you saw, across all of physics and using a lot of different mathematics. We can't be experts across everything, so we're really always looking for people with expertise in different areas of physics or mathematics to help us out. We're looking for collaborations and looking for editors, journals, and conferences that are sympathetic to the mission. It's been surprisingly challenging to find journals that are really a good fit for a lot of these sort of cross-cutting or foundational work in physics, just because people aren't really writing papers about the principle of least action since it's a couple hundred years old. So we're looking for opportunities to publish and to advertise the program at different conferences. All right, thank you very much. We can move to the Q&A.
Yeah, so remind people that if they want to write the question, they can put it in the question and answer, or they can raise their hand and then we can go and do it in more interactive. So there is one hand. Go Sebastian.
You're muted.
Yes, he's muted.
Oh, sorry, I was just trying to see where the Q&A. I don't know if I raised my hand accidentally or something. Oh yeah, I think I
Okay.
did. Sorry.
Okay.
Yeah, I'm trying to understand how the Q&A works. I see here the chat, but I was not seeing any question.
Okay.
Thanks.
Okay, so there is a question here. Professor Idala, there was an insightful talk. I have a question about the linearity in quantum mechanics. Doesn't Wigner's theorem make linear unitary dynamics already forced by the inner product structure? You want me to answer this directly?
Sure, you can go ahead.
So the linearity of the inner product, it's essentially a, how can I say? It's a convenience. Like the real physical output is from the Bohr rule, and the Bohr rule is quadratic. So you can have an inner product, which wouldn't be an inner product, that it's non-linear because it introduces phases that are essentially non-linear, but so the inner product is ruined, let's say, but the Born rule is recovered. So you kind of would need a new Wigner theorem that would be more generalized, that wouldn't assume that you have a linearity of the inner product. But once you say, I want a representation that is linear because I can have a representation that is linear, and why would I want a representation that is nonlinear? Why would I want to make my my life harder? Then you have the Wigner theorem that tells you, okay, now all the transformation is going to be unitary within that inner product. But again, when you know that everything is defined up to a phase, right? So when you're going to make a change in phase, you are basically redefining the inner product. And so technically you have different linear spaces that are all equivalent, and you can go from one to the other. So I hope that answers Alexi. How come the physical verifiability implies topologies in sigma algebra? The families of open sets and measurable set. So that I think we're gonna look in more in detail tomorrow. That Tobias is gonna talk about it. But effectively, open sets are verifiable statements. So you can say, when you say the position is within this bound, that bound is an open set. So you say the position is between 0 and 1 meter, you have to take that as an open set. And then the idea is that the operation that you have in the topology corresponds to logical operations that you have on the verifiable statement. And again, we'll see that more in detail tomorrow.
So you're never going to verify a continuous quantity with infinite precision of a real number, right? So you're always going to have a range plus or minus something.
Right, and so the single point, it's a falsifiable statement. You can test that the math of the photon is not exactly zero if you're able to prove that it's within a range that excludes zero, but you're never going to be able to verify that it's exactly zero. So the singleton zero is a closed set, so it's a falsifiable statement. It's not an open set. So all these things are going to map very well, and it's kind of amazing that they map very well. Then Zoe references the superposition in multi-decomposition slide. how, if it does, distinguishability of preparation relate to determinism? A separate question. Okay, let's start with that.
Let me go back to the slide. A little slow here. There we go. Now that's the question. Well, how does it relate to, so here's the superposition as multi-decomposition slide. How, if it does distinguishability of preparations relate to determinism? So the Schrodinger equation describes deterministic and reversible evolution. You are thinking about what people talk about wave function collapse of states that are in a superposition to something that it's one of the decomposed states. I think of it as related to the zero entropy bound and the minimal that you don't have zero variability in your system, rather than directly related to that. Maybe Gabriel, you want to say?
Yeah, so it's basically a separate problem, right? Because determinism, reversibility, it's a relationship between states and preparations and measurement at different times. The multi-decomposition is a property at a single time. You say this preparation, like this preparation defined over these two states, and this preparation defined on these two states are indistinguishable. So when you are at a particular time, you can tell whether I prepared it in one way or another way. So it's really a property of the space of statistical ensembles at a particular time. Then how it's mapped in the future or in the past, it's basically a disconnected thing. And then a separate question I have.
Yeah, I was going to read the next question. Go ahead.
Yeah. I have is, why can we not approximate physical dimensions, since we can always make our measurements more exact?
Yeah, I mean, you're never going to make a length into an area, right? Or a volume into an area. So it's not about measurements being more exact. It's really that like an area is never going to be a length. A volume is never going to be an area. A hypervolume is never going to be, n to the whatever if you're in, many three-dimensional space, but then you have n for many particles in statistical mechanics. So you have you're raising to the nth power because of your Avogadro's number or whatever. But the hypervolume in phase space is never going to be a large hypervolume of one smaller dimension. So it's really the fact that it's physical dimensions. So if just intuitively for low dimensions, you can think that a length is never going to be an area, is never going to be a volume.
One way that I think about it is that the unit and therefore the physical dimension selects what type of measurement you're making. So if you're making a measurement of length, it's completely different than making a measurement of area. So you don't have like a continuum of measurements between the measurements of length and the measurements of area. So if you had a family of possible measurements for which you are changing the dimension continuously and n to the other, then you can probably do that. But that's not how physics work. We don't really have that. So if we were able to measure fractal dimension, for example, and have measurements that depend on fractal dimension, then yes, but I wouldn't know how to do that operationally. Okay, next one. Can we use this assumption to extend this to non-equilibrium thermodynamics or approximately random processes? Bromian motion comes to mind. I'm curious if this investigation can help with analysis of chaotic system, a better mathematics for it. Many physics demand it, like phase transition and so on.
So we can definitely extend the reverse physics approach to non-equilibrium thermodynamics or approximately random processes. That's something we have not spent time on in any serious way yet. We are trying to do sort of the core classical mechanics, quantum mechanics, thermodynamics, statistical mechanics before we move on to other things. But if others have expertise in that area and ideas, we would be happy to work with them now, right? We're happy to be responsive to people who have ideas and expertise. But I think we'll do non-equilibrium thermodynamics after we're satisfied that we've fully understood equilibrium thermodynamics. But yeah, the approach should apply to everything, right? It's a long game. We are slowly trying to do this for all of our established theories across physics.
And for non-equilibrium thermodynamics specifically, one of the problem is that there are a lot of approaches that are being developed that it's not clear that they work on the same operating assumptions. So we were just at a conference last week, and there was somebody who was showing this that there are all these different definition of work that essentially work under different assumptions. So the idea would be to start once you have a firm ground of equilibrium thermodynamic, which as Christine was saying, we still don't have that. The extension would be, okay, we are non-equilibrium, but is there such a thing as non-equilibrium, or there are different kind of non-equilibrium? And at that point, it would be a way to say, okay, you can have under this assumption you have this type of non-equilibrium. Under this assumption you have this type of non-equilibrium, because at that point, equilibrium is kind of one, but once you start making this perturbation, you might actually have different theories. And again, if all this would be done properly, then we would have a lot more clear ideas of where the boundaries are, because I know for a fact that in non-equilibrium thermodynamics, and there are different notion of entropies, and there are kind of people talking past each other because they have different implicit assumptions. So even just taking the assumptions out would be helpful. Okay, next one. Based on the current expansion rate, the cosmic microwave background, the radiation patterns, and the distribution of dark matter, can we reconstruct the exact physical conditions, temperature, density, and quantum fluctuation at the moment of the Planck epoch using GR? Also, by using quantum models, can we reconstruct the background geometry of space-time, the cause, simply by observing the entanglement entropy patterns of quantum field the effect?
So these are well beyond what we're working on now. We think before people try to ask such a question, we think it's important to go back and ask what allows you to define a temperature, for example, what allows you to define a density already assumes that you have some notion of volume, like a density over what, right? And so we are far from trying to do something like that, and that wouldn't, in reverse physics, that wouldn't be how we would approach it. We would want to go back and say, what are the conditions under which you can define this quantity, that quantity, the distances, angles, time, and then go and look at the assumptions in a theory like GR, in quantum field theories. Once we get to those, we are not focused on them now. We want to go back and understand first all the assumptions that are built into non-relativistic quantum mechanics, for example. And then see if that kind of question makes sense, or maybe GR already has it built in that you can't define some of the things that you're asking about there. So I guess it's similar for the second question, using quantum models. Can we reconstruct the background geometry of space-time simply by observing the entanglement entropy patterns of quantum fields? So yeah, we we'll get to quantum fields. I don't think we'll get to cosmology very soon, but I hope we get to field theories in the next few years. And so we would be approaching it somewhat differently, but then might have a response to that question once we do more work on quantum field theories.
Okay, next question. Could you explain more about how this is different from a theory of everything?
So the theory of everything is effectively a reduction, the way people talk about it, like what people typically, I don't know that people all mean exactly the same thing when they talk about the theory of everything, because we don't have anything that people think is the theory or a theory of everything. So it's not clear that they all mean the same thing. But in general, it's a reductionist picture. And it's basically the unified theory of gravity and all quantum field theories. Um, and so we don't um we don't so if reverse or assumptions of physics doesn't have a reductionist approach, as I mentioned. We don't think of one physical theory as more fundamental than others. It's really about a bunch of, we think of a physical theory as modeling things in nature, and you're going to have a bunch of different physical theories that are modeling different things in nature and have different realms of applicability. And so um, it's not that there's one theory of everything. Even if you just think of quantum field theory and the flow of water in a river or something, right? I think people who work on theories of everything think that they could describe the flow of a river from quantum field theory equations, which is not obvious to me just because of there's a famous quote that more is different. So complex systems really exhibit emergent behaviors. Um, so that just thinking of our existing quantum field theories in the standard model of particle physics, I think there's actually a lot of phenomena that by themselves they can't describe because of the way they're built. And so reverse physics is trying to understand what are the assumptions that you already built in implicitly into the mathematical structures of your different theories. And so we need to be really explicit about where they're applicable and where they're not, and we're not trying to find a single theory that's going to be describing all that we're actually going to use to describe all or model all phenomena observed. Um, our base theory would be a collection of uh, requirements or physical assumptions that have to be true for any physical theory, but they're not going to be sufficient to usefully model. You will need additional assumptions to usefully model different things in nature. Gabriel, do you want to add to that?
Yeah, so if you have if you know a little bit of math or even computer science, so the idea is that we're not trying to find, let's say every physical theory has a notion of state, right? And the theory of everything is trying to find the true state, right? A definition of states that works everywhere, right? And then every other state that you have in classical mechanics, quantum field theory is going to be an approximation of that, right? That's not how math works. For example, you are not trying to find the mathematical object that it's the true mathematical objects, right? You have sets, you have numbers, you have topological spaces, right? Everything is a set, and then if you have a topological space, well, that's a set plus some other structure. If you have a group, that's a set plus some other structure, right? There is no fundamental category that is everything is that in some approximative sense. So that's what we're trying to do with physics, reverse physics as well. We want to have a notion of state that has the common characteristic of all possible states in all physical theory. And then we're going to have a specific specialization of that. So you're going to have the classical state. Well, the classical state, it's like an abstract state, but a little bit more refined with more structure. And the quantum state is also like the general state, but with more structure. As you saw at the beginning, we saw that deterministic and reversible evolution, both in classical and quantum mechanics, gives you some notion of Hamiltonian evolution. Right? What we'd like to have in reverse physics is an abstract notion of state and an abstract notion of process, such that if we say that the process is deterministic, we kind of have sort of a more general type of Hamiltonian evolution. And then when you say, oh, but I have a classical state, you get classical Hamiltonian mechanics. And when you say I have a quantum state, you get quantum, the Schrödinger equation. So the idea is that we can push up to more general structure, the theorems and the description, and then have all these different instances. But when we have this generalized idea, the generalized idea is exactly right in all the different theory, right? The general theory, the theory of everything goes by approximation. All the other things are true in some type of approximation. When we are generalizing theorems instead, no, it's true exactly in all the specifics, and that sort of is more like how the foundation of math works. It's like looks like a class diagram if you have done object-oriented programming. It's more similar to these type of things. So there
Now
is a
maybe add
follow-up.
another example.
Go ahead. Yes.
So if you think about thermodynamics, when they developed it, they didn't know about statistical mechanics, right? In statistical mechanics, you say you have actual particles, they have some velocities, momenta, you take distributions. And then in the thermodynamic limit, you can forget about the exact state of all the particles and you just have a temperature and a volume and stuff like that, right? So they were doing thermodynamics on like a higher level. They just described what they could do in a lab. They could measure a temperature, they could put heat in it, they can get work out of it and that kind of stuff. And the theory of everything at that time was just classical mechanics. Like classical mechanics, they thought was the theory of everything. It describes exactly what each particle is doing. I just need to know the position and the velocity of each of them. And you can, of course, then like statistical mechanics then is finding thermodynamics based on that theory of everything. But then now we know you can just put quantum mechanics below it. That is now your theory of everything. And then the thermodynamic limit, and if you're at high entropy, you end up at the same thermodynamics. So it's basically an example where you put two theories of everything below thermodynamics that lead to the same physics. At least if you just consider thermodynamics, right? So basically what we want to do is like we don't pick which one is the theory of everything. We just describe what you can actually do in the lab. So we would take the perspective of just thermodynamics, where you ignore where it comes from. And yeah, it's basically a concrete example where you don't care about the specific theory or everything and just describe on the higher level based on what you can do, what mathematical structures you need. So thermodynamics would be, well, you need three variables, you have an entropy and stuff like that.
Good. I hope we answered the question. Let's go to Blake. Do you have a sense in which assumptions lead to notion of locality? Would it be an assumption itself?
Yeah, so infinitesimal reducibility, I would say effectively implies locality, right? So you can, in the theory of classical mechanics, it's built in that you can identify points in phase space or your states with mathematically infinite precision, right? So really, yeah, infinitely precise. And then irreducibility, relevant for quantum mechanics, has non-locality built in. So the fact that I can't track what's going on with the upper back left corner of an electron means that I have to get some kind of non-local effects because of that, right? So because if I could localize what's happening to some part of the electron, then that would violate the assumption of not having any information about what's going on with different parts of the electron. And so I think the infinitesimal reducibility is the core assumption related to locality. And we already know that we have phenomena in nature that where that's not a good treatment. Gabriel, do you want to add more?
Yeah, we can add, when we saw the classical uncertainty principle, that we have this probability distribution and put a lower bound, we already saw that that leads to a notion of a classical uncertainty principle. That's basically what Christine is saying, right? So in classical mechanics, if you assume that these Gaussian can become more and more picked so that you can go to minus infinite entropy, then you can always resolve the distribution at a finer and finer precision. But if you start putting a lower bound on the entropy, then it means that you put a lower bound on the uncertainty, and now your distribution has to be spread somewhere. So it has to be spread either in position or in momentum. And of course, if it's spread in momentum, then it means that it's going to spread in position over time anyway. And that's basically why you must have it.
So in that sense, non-locality is implied already by the third law, or non-local phenomena, non-local behavior for some systems in nature is already implied by the third law of thermodynamics, that you can't have less than zero entropy.
It is important to note that this notion of non-locality comes from the lack of reliably being able to prepare systems. So it's something that the physics has to have. So when we describe systems, we cannot go to that level of precision. So our physical laws cannot go to a level of precision that is bigger than that, because otherwise it would imply that we would be able to make preparations that are violating the third law. But that doesn't mean that there is some type of ontological pictures related to that, right? We are only talking about what can we reliably prepare and reliably measure, such that we can make physical laws about such things, and the notion of non-locality, or this type of non-locality that we talk about, it's at that level. But again, going back to another thing that was on the slide, the fact that we cannot make those determinations means that there is no physical process that allows us to make that determination, which still is a statement about processes that exist in the world, right? So it's not just oh, we can't do it. No, there are no processes that allow us to do if that's true. Then a query: is there a mathematical way to decompress from macro to micro complex systems to see their hidden rules structure? Or is there this process of emergence for fundamentally irreversible, or we don't even know it yet?
Taking complex systems, a mathematical way to decompress from macro to micro to see the hidden rules of complex.
Let me answer that then.
Yeah.
One of the things that it's important to us is that again, there is no single level of description that works for everything. There are going to be multiple level of descriptions at different steps, right? So, for example, we can take a buckyball or a very complex molecule and do diffraction experiments. And during those diffraction experiments, we treat this very, very complicated system as a single quantum pure state using the same equations, right? That's what we do. The same things for atom and the same thing for a single electron. So you have cases in which the same different systems use the same mathematical equations to be able to be described. So for us, that's interesting, because what happens is that to be able to treat a complex molecule as a single quantum system, it means that the internal structure in those particular circumstances is completely irrelevant, right? So how do you map sort of the higher level description to their lower level description and constituents? That's a very interesting process, but it doesn't always have to be something that, let's say, emerges from, that can be described from below. It could be that it's described from the above. So let's say a proton, right? It's a spin 1/2 particle, such in the same way that the electron is a spin 1/2 particle, and you could say that it's it's how all the quarks and gluon interaction and so on make it a spin 1/2 particle, or you can just say, well, now that I'm treating this whole complicated system in this way, I will have some of these symmetries, and then it's these symmetries that are responsible for the fact that I can treat the proton as a single spin 1/2 particle. So these type of statements and relationships and so on, these are all things that we still have open in the back of our mind, and how is it that a very complicated object can be still, in some cases, treated as single pure quantum state? That's something that me personally find fascinating, and I have no idea how that works. These would be the things that I would be interested in understanding, and I have no answer yet.
Maybe I can use my example just again, because if I understand the question correctly, you have a macro state, the thermodynamic state, for example, and you are asking, can I find out what is happening inside? What is the hidden structure, the hidden rules of like how this macro state is built and how it evolves and blah, blah, blah. Well, I think the example is like, yeah, you can consider this to be a classical state, or you can consider it to be a quantum state. Or you can even consider particles, like the individual particle is an atom that you describe by quantum, but then you just treat it as one particle, which is you then treat classically. And all of this doesn't matter. So at the macro level, it looks the same, but the micro level is completely different. So I don't think there is a mathematical magic trick to just go backwards somehow. Like mathematics sometimes feels like magic, but they can't do like it can't know what is going on. The data is just not there. So I think this is a very common thing. I think even in economics, like they had to learn the hard way that they cannot go from macro to micro. And I think they're still trying, but like you can put different microscopic descriptions that lead to the same macro physics, and so it's like not determined.
Right. In the same, my same example, right? The macro dynamic of a proton and the one of a complicated molecule is different, but in some cases I'm still using the same quantum object. So there is not enough information. I guess that's the more precise way to say it. Okay, Aditya, does reverse physics have any further insight to the assumptions needed for relativity, like why space-time takes the form that it does and that Lorentz boosts are linear?
We'll talk more about relativistic mechanics in the second lecture. Yeah, we'll talk more about relativistic mechanics in the next lecture. I don't know. Do you want to say anything right now?
Well, basically what we'll see is that the sort of parts of relativity emerge just by asking for deterministic and reversible processes that are time dependent. And if you want to use the time dependence correctly, then you have to extend the phase space, and not just with position momentum, you have to extend it with time and energy. And once you do that, certain structures are inevitable. And then, if we assume full kinematic equivalence, then the metric tensor pops up. So, in a sense, relativity is there to treat time-dependent processes correctly. It's not an extra assumption. In fact, in some sense, Galilean transformation are wrong because they don't give you the correct quantum states, and they don't give you an invariant entropy. But we'll see a little bit less, in the next lecture. And then Jacob, and there is also a follow-up. Why does the third law imply non-locality, and what does it imply in other ways? Maybe to the positive value of entropy implied by the third law of thermodynamics, which leads to uncertainty in classical mechanics. Yes, that's basically it.
The fact that the third law of thermodynamics says that the entropy cannot be negative, so it's to be greater than or equal to 0. And so if you think of entropy just in classical mechanics related to count of states, areas, and phase space, you can't go beyond some minimal area according to thermodynamics, even though classical mechanics without thermodynamics allows you to go to arbitrarily small points in phase space. So we showed how the uncertainty principle that you have some range in position, momentum, delta Q, delta P, coming from a lower bound on the entropy. So
And if you want to picture it more physically, if you imagine that you have some preparation device that spits out an electron or a particle with at some position with particular velocity, the problem is that that device is always interacting with everything else. So you can't shield and make a perfect preparation. You're always going to have some jitter because it's still going to, interacting with somebody on Andromeda moved the furniture and a wave came and somehow jiggled your preparation device, right? You can't completely and perfectly isolate, so there is always going to be a jitter. And so whenever you're making these relationship between preparation and the final measurement, you're always going to have some jitter in your description. Your description is never going to be precise because you can't test and can't prepare and can't control at the level. And again, since there can't be a process that gives you that type of control, then it means that in the physical system you can't even define things at an infinite level of precision, because otherwise you would have a process that gives you that level of control, and therefore you violate the assumption that we have. Okay, so we should take a 5 minutes break to give the speaker 5 minutes to wind down, and then we are gonna come back in 5 minutes with the next session. Okay, so let's start the second lecture for today, and we're gonna see some results in reverse physics. Christine?
All right. Yes, so we're going to go through a handful of results from reverse physics in more detail. So what we have most developed within reverse physics is classical mechanics. So first, let me give you an overview of reverse physics results for classical mechanics, and then we'll go into a couple things in more detail. So as mentioned in the previous lecture, for those who were there, one of our two core assumptions for all of classical physics is infinitesimal reducibility. The state of the system is reducible to the state of its infinitesimal parts. That is, specifying the state of the whole system is equivalent to specifying the state of its parts, which in turn is equivalent to specifying the state of its subparts, and so on. So a classical state is a distribution over the states of infinitesimal parts. The other core assumption underlying all of classical mechanics is that of independent degrees of freedom. So the system is decomposable into independent degrees of freedom. That is, the variables that describe the state can be divided into groups that have independent definition, units, and count of states. So this assumption recovers pairs of conjugate variables for each degree of freedom, recovers frame invariant entropy, and frame invariant count of states. In addition to these two physical assumptions that apply across all of classical mechanics, we can choose to assume determinism and reversibility. The system undergoes deterministic and reversible evolution in time. That is, specifying the state of the system at a particular time is equivalent to specifying the state at a future time, this is determinism, or a past time, this is reversibility. And so the conservation of entropy, the conservation of count of states, plus degree of freedom independence recovers Hamiltonian evolution. Another assumption we can choose to make that recovers other parts of classical mechanics is kinematic equivalence. The kinematics of the system is sufficient to reconstruct its dynamics and vice versa. That is, specifying the motion of the system is equivalent to specifying its state and evolution. So this links trajectories in physical space with dynamics in state space, recovering inertia, masses, and scalar and vector potential forces. And so to create a Venn diagram, so all of classical mechanics has these assumptions of infinitesimal reducibility and independence of degrees of freedom. We can then add, and we call this just classical mechanics, CM. So this plus kinematic equivalence gives us Newtonian mechanics. Infinitesimal reducibility and independence of degrees of freedom plus deterministic and reversible evolution give us Hamiltonian mechanics. And if we have both kinematic equivalence and deterministic and reversible evolution, then we get Lagrangian mechanics. So it's basically the intersection of Newtonian and Hamiltonian mechanics. We like to look at things in different ways. I showed this in the last lecture. So rather than a Venn diagram, we can make a diagram like this. So we have at the bottom our infinitesimal reducibility and independence of degrees of freedom that are relevant for all of classical mechanics. So classical states. So classical states plus what we call weak kinematic equivalence, which is that there exists an invertible map between conjugate momentum and velocity. If we assume that, and classical states, this leads to Newtonian mechanics. If we assume classical states plus deterministic and reversible time evolution, this leads to Hamiltonian mechanics. If instead, and if we have Newtonian mechanics plus Hamiltonian mechanics, this leads to Lagrangian mechanics. Lagrangian mechanics, where we have our invertible map between conjugate momentum and velocity that's also linear, gives us massive particles under potential forces, which wasn't called out separately in the Venn diagram on the previous slide, for example. And each assumption is an equivalence class of multiple conditions. So just to read a few of these, there's a linear relationship between conjugate momentum and velocity. So this is full kinematic equivalence. At each position, there exists a local inertial frame. This is an equivalent way of expressing this, full kinematic equivalence. The position fully defines the units of all state variables and therefore an invertible transformation between momentum velocity. Again, this is another formulation that's equivalent to express full kinematic equivalence. And being able to express things in all these different ways and see these types of diagrams or the Venn diagram on the previous slide give us insight into all the logical relationships between the different physical assumptions and the different physical theories. Yet another way of looking at it would be a diagram like this. So we have here our foundational assumptions for all of classical mechanics, that of infinitesimal reducibility, so that you can studying the state or the dynamics rather of the whole system is equivalent to studying the dynamics of all the possible subparts, infinitesimally small, that you could mark or label. And then independence of degrees of freedom. So I can, across degrees of freedom, I can factorize things basically. And that we have classical phase space that comes from, as mentioned briefly in the previous lecture, comes from requiring that count of states and distributions and densities be invariant under coordinate transformations. So we have classical states expressed in classical phase space, and then we add the assumption, if we add the assumption of determinism reversibility, we'll get Hamiltonian mechanics. If we add the assumption of weak kinematic equivalence, we get Lagrangian mechanics, a full kinematic equivalence, we get massive particles under potential forces. So there are a lot of different ways of looking at this, and we think that having all these different ways of looking at the different assumptions in a theory with these equivalence classes of different formulations, different mathematical and physical expressions of them, or these different diagrams laying out logical relationships among the different theories within classical mechanics in this case, and the different assumptions gives you a lot of insight looking at different theories. So to dive,
Christine,
yeah,
a small technical problem. Your audio and camera are went out of sync. If you go to OBS in the camera and you disable and re-enable, it will go back in sync.
okay, is it in sync now? I stopped and started the virtual camera.
No, not the virtual camera. You have to go in the scene with the camera, open up the camera and say disable or enable. If you can do it well, otherwise we'll just skip, but it's very annoying.
Sorry, so into the scene collection.
Yeah, you get the scene with the full camera.
Full camera,
Sorry,
okay.
everybody.
Yes, okay, I got the scene with the full camera.
Okay, now select the camera in the items, in the
Sources,
sources.
yeah,
Yes, open it up,
okay.
enable it and disable it.
So, so I'm opening the camera source. Oh, so deactivate and reactivate.
Yes.
Okay. Okay.
Okay, good. It
Is
went
that
back.
fixed? Okay.
Yep. Sorry about that.
That's okay. Thank you for telling me. I would not have known. All right, so we're going to dive into one of these in more detail, performing reverse physics on the principle of least action for 1 degree of freedom. And so the required background for this section of the lecture is Hamiltonian mechanics, so specifically Hamilton's equations, Lagrangian mechanics, so that the action is the integral of the Lagrangian in time over a given path, integral of the Lagrangian in time over some path gamma, that actual evolutions are the paths that make the action stationary, so the variation of the action is 0, that the Lagrangian is the Legendre transform of the Hamiltonian. You can express the Lagrangian as PQ dot minus the Hamiltonian. And then we'll also need elements of vector calculus. So given a vector field V, a field line of the vector field is a line always tangent to the field. And the divergence of a vector field is the flow of the field through an infinitesimal closed region. And a divergence-free field, del dot field equals 0, admits a vector potential such that the field can be expressed as the curl of the vector potential. So you might have seen that the Lagrangian can be written as the difference between the kinetic and potential energy. This, however, does not always work. So for example, the Lagrangian for a particle with charge q, we would have 1/2 mv squared plus qv dot a. This is the velocity of the particle. This is the vector potential of the magnetic field, minus q, the charge, times the electric potential of my field, my charged particle moving in an electromagnetic field. And so this is clearly a kinetic term, this is clearly a potential term, but we have this term in the middle that has a velocity, so this seems kinetic, but it has also the vector potential, so this seems like it should be a potential term. So this does not work in general, even though the action is always going to be the Lagrangian, the integral of the Lagrangian in time over a path. So to perform reverse physics on the principle of least action, we'll be working in phase space extended by time. So we have Q and P, our position and momentum, and then we have our time axis. We have what we call the displacement field. So this is just the time derivatives of position, momentum, and time. This is going to be 1, but I've written it out so you can see clearly how it relates to the other 2. And so basically this is states, the dynamics of states, so they're moving around in phase space as a function in time, as a function of time. So an evolution, a path of a state in this phase space extended by time, we write as gamma, so it's position as a function of time, conjugate momentum as a function of time, and then time. So time, note that time is both a parameter and a variable. And the actual evolutions taken by a particle are field lines of this displacement field. And so the field lines are always tangent to the field. In general, for any vector field, the field lines are always tangent to the vector field. So we have these possible trajectories in phase space, possible evolutions in phase space, and I've labeled one of them gamma here. So if I assume deterministic and reversible evolution, then no states are lost or created. The count of states is preserved in time. You can also think about this as areas or volumes in phase space being conserved as a function of time. So if I have as many states going into a region in phase space as going out, as they evolve in time, this means I have a divergence-free field, so my displacement field, so the flow of states is a divergence-free field, so del dot my displacement field, which again is here, is equal to 0. So if I have a divergence-free field, then this admits a vector potential. So I can express my flow of states, my vector field describing the flow of states in phase space extended by time, as the curl of this vector potential, which we've chosen to call theta. And the minus sign is added here just to match conventions, which we'll see later. So I can write my vector potential just in terms of components. So it's got a position component, a conjugate momentum component, and a time component. I can choose a gauge. Remember that the vector potential is not physical. What's physical is the flow of states in time, in phase space. And so the curl has to remain unchanged, but I can change my theta as long as it doesn't change the curl. And so I can choose a gauge in any way I want that doesn't affect the curl, that doesn't affect the physical flow of states. So without loss of generality, I can set my momentum component of my vector potential to be 0. Then I I know that my displacement field, the time component, is just dt dt. Remember, time is serving both as a variable and as a parameter. And so this is 1. The third component is going to be 1. So I have S, the time component of the displacement field, has to be generated from the curl of its vector potential. So this would be the partial p theta q minus partial q theta p. And so this must equal 1. So I can solve this and find that theta q must equal p, the conjugate momentum. And then I can rename my time component to this symbol capital H, and I'm putting a minus sign there as well, related to conventions later. So without loss of generality, I can express my displacement field, my physical flow of states in phase space extended by time, as minus the curl of this vector potential, with the vector potential written as momentum 0 for the momentum component. So the momentum is the spatial component, or the position component, the 0 as the momentum component, and this minus h as my time component. So I've just rewritten that here, so we remember it. So now I can look, so I know that I defined my theta as the vector potential for my physical displacement field. And so I can express all the components of my displacement field. So the position component is dq dt. I can write this as the curl term in my vector potential, in terms of my vector potential. So with this form of the vector potential, I get that dq dt is dh dp, partial h partial p. My dp dt, so this term I can write out the curl, write it as the curl of my vector potential, and I see that dp dt is minus partial h partial q. And I see that the time component here, dt dt, which must equal 1, gives, I get this relationship here. And so I recover Hamilton's equations this way. So I have started from phase space extended by time, written the flow of states, assuming deterministic and reversible evolution, which made it a divergence-free field. No states were created or lost in time. So this flow of states was divergenceless, admitted a vector potential, and without loss of generality, I can express it this way, and then I recover Hamilton's equations. So we're talking about the action principle specifically. So if I take the line integral of my vector potential field for the flow of states, so I have the integral of the vector potential over some path gamma. I can express this in terms of components. So I'm going to write out the expression I had for my vector potential. So momentum 0 and minus h, which we just saw, turned out to be the Hamiltonian. And we saw that we recovered Hamilton's equations. And then my gamma, I'm going to write as a dq dt, dp dt, dt dt. But we can express this as, if I now just do the dot product here, I have p dq dt, 0 times this term, and minus h dt dt, which is 1. So I get p dq dt minus h. You might recognize this as the Lagrangian. So the Lagrangian is the Legendre transform of the Hamiltonian. And so I have the action, so that this is now the Lagrangian integrated in time over some path gamma. So this is the action. So the action is, what it is the line integral of the vector potential of the flow of states with deterministic and reversible evolution. This is going to be unphysical because it involves a vector potential. But now we can look at the flow between some path gamma and a variation on that path, gamma prime. So here's my path gamma. Here's my nearby path, my varied path, gamma prime. So I have the same endpoints, right? Starting and ending point. So this creates a surface between the path and its variation. So I can look at the flow of states through the surface, the flux, basically, the flux of states through a surface. and write it this way. So I have the flow of states represented by the displacement field. Displacement field S is the flow of states in phase space extended by time, and then it's dotted through this surface between the path and its variation. I can re-express the displacement field, the flow of states, as the curl of the vector potential. And then I can take this expression and apply Stokes' theorem. So the curl of the vector potential dotted through the surface enclosed by the path and its variation. I can write this as a line integral around the boundary of the surface. So, the curl has just become the vector potential itself. So this is from Stokes' theorem. So now I can write this out, the closed boundary, in terms of taking the integral along the path in one direction and then minus the path, the varied path, to form this closed boundary integral. And so this is now the variation of theta dot d gamma. All right, so this difference in the paths is the variation. So it's the variation. We said on the previous slide that the integral of theta dot d gamma was actually the integral of the Lagrangian in time. And so it's the variation of the Lagrangian in time. So it's the variation of the action. So the variation of the action is the flow of states in phase space extended by time between the path and its variation. So if the path gamma is an evolution of the system, then the flow is going to be tangent to the path itself. And so our area between the path and its variation goes to 0 because we have this tangent flow, and therefore the flux of states through it is 0. If the path gamma is not an evolution of the system, we can find a variation gamma prime such that this variation is non-zero. So the action is going to be stationary. It's going to have 0 variation over and only over actual evolutions of our states. So the action principle, the principle of stationary action, is really a way of mathematically requiring deterministic and reversible evolution of states in phase space, of classical states. And the action itself is not physical, but the variation of the action is. So yeah, we think it would be much better if this were discussed much more clearly in textbooks. A lot of discussions about, what is the action, sort of making things much more complicated than they need to be, rather than just saying this is a convenient mathematical way to enforce deterministic and reversible evolution of a classical state in phase space. So assuming 1 degree of freedom of classical phase space, deterministic and reversible evolution, and you need kinematic equivalence here because you're defining a Lagrangian as well. So you need to be able to express your conjugate momentum in terms of velocity. And these 3 assumptions are equivalent to the principle of stationary action. So moving on to relativistic mechanics. Now, the required background for this section is special relativity. So that's the fact that space and time coordinates get grouped together in special relativity. And so we'll be using Greek indices for 4 vectors and Roman indices for 3 vectors. So our position for the vector is CT and the QIs. The metric tensor G alpha beta defines the geometry of space-time, so lengths and angles in space-time. We'll be using the minus plus 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 convention. So path length squared equals minus dt squared plus dx squared plus dy squared plus dz squared. Energy and momentum get grouped together in special relativity to form momentum. So your P alpha is minus E over C, and then the PIs. The for velocity is velocity with respect to proper time, that is time in the rest frame, and its norm is minus c squared. So for velocity will be denoted with u, again, a Greek index for 4 vectors. So it equals d proper time, dq, d position, d proper time, or d position 4 vector, d proper time, and then its norm, so u alpha, g alpha, beta, u beta is minus c squared. And for a free particle, the relationship between 4 momentum and 4 velocity is this. So p lower beta, g beta alpha equals p upper alpha, and this is equal to the mass times the 4 velocity. All right, so we want to extend Hamiltonian mechanics to handle changes of coordinates that mix space and time variables. So the question is how can we do this properly? So we have we're going to write a 4 vector just with time and the typical 3 vector if we have 3 spatial dimensions. But we're going to introduce, we're going to separate time the variable from time the parameter. In my derivation of, or my applying reverse physics to better understand the principle of stationary action, we had phase space extended by time, but we used time as both a variable and a parameter. Here, to handle changes of coordinates that mix space and time variables properly, we're going to have to separate time the variable from time the parameter. So we have time, the variable that we can express as a function of time the parameter. You can also think of this as an affine parameter. And we have our QIs that are a function of this affine parameter as well. So we're going to do Hamiltonian mechanics on extended phase space. So recall that we had before our vector potential for the flow of states in phase space extended by time, and the time-like component was the minus the Hamiltonian. We see, I don't show it in detail here, that the only possible choice for conjugate 4 vector to our Q alphas is going to be minus E, which is going to be equal to the Hamiltonian for valid states. And then we still have our usual conjugate momentum. And then our Hamilton's equations in the extended phase space. So we're writing our Hamiltonian in extended phase space as this cursive H. So different font, note these 2 different symbols here. They mean different things. So our dq alpha ds with respect to this affine parameter is going to be the partial derivative of the extended Hamiltonian with respect to our 4 momentum. dp alpha ds is minus the extended Hamiltonian dq alpha. And we have a Hamiltonian constraint now that will describe the relationship among these 4 variables. So we had our time and QIs from our Q alpha and our energy and PIs from our P alpha. And it's going to equal 0. So this isn't just a conserved quantity. It's not just about conserving energy. This valid states are going to have to maintain this Hamiltonian constraint relationship between whatever, you can have different Hamiltonians for different physical systems, of course, but working in the extended phase space, you're always going to have this extended Hamiltonian, this Hamiltonian constraint be equal to 0. So we're enforcing certain relationships among these variables that are the ones that are, that's what we must have to have valid states. So again, we have our Q alphas and our P alphas. We can now write the symplectic form of classical mechanics in our extended phase space. So we have our dqi, dpi as usual, but now we have a minus dt, de. So the energy momentum covector and the negative sign for the temporal degree of freedom appear in the extended phase space without any knowledge of space-time geometry or the speed of light c. So this tells us that Lorentzian relativity is the only correct way of handling handling coordinate changes that mix time and space. So it extends the count of configurations per degree of freedom to the temporal degree of freedom in the correct way. And you can still think geometrically. So this diagram, I didn't show it before, but this would be relevant also for Hamiltonian mechanics not on phase space extended by time. But if we have, say, 2 different degrees of freedom, so I can equal 1 or 2, so then my symplectic form would be dq1 dp1 plus dq2 dp2. And we can get a visual or geometric representation of this related to the Pythagorean theorem. So if I have my dq1 dp1 and my dq2 dp2, then my symplectic form has this area here. Independent degrees of freedom are orthogonal. Again, this is in general, not specifically on phase space extended by time. But now when I'm thinking about handling time properly for coordinate transformations that might mix space and time, if I want to relate the temporal component to the symplectic form, then I'm going to have, and I'm doing this for 1 degree of freedom, otherwise I couldn't represent things very nicely on a flat slide. But I still have my dq1, dp1, and now I have minus dt, dE. And so I can re-express this to not have a minus sign. So if I have my dq1 dp1 equals now the symplectic form plus dt dE. So I still have a Pythagorean formula, but note that if I'm involving both the position momentum and the temporal degree of freedom, then your symplectic form is no longer the hypotenuse, it's one of the sides of your triangle. So we're counting states at equal time, and this is what leads the temporal degree of freedom to be orthogonal to the symplectic form on the extended phase space. So to look at an example with a particular Hamiltonian or extended Hamiltonian, so this is our Hamiltonian constraint. So for a free particle in an inertial frame, here is my Hamiltonian constraint. So I have my, 1 over 2m, I have my 3 momentum, or whatever number of spatial dimensions I'm in. I have this was from the temporal component of the 4 momentum, and then I have an m squared c squared for free particle in an inertial frame. This Hamiltonian constraint is going to be the generator for proper time. So it comes out that the affine parameter s, when we separated time the variable from time the parameter, we'll see it corresponds to proper time. So if I work with my Hamilton equations in phase space extended by time, where we've separated time the parameter from time the variable from time the parameter. So my dt ds, so the derivative of time the variable with respect to the affine parameter, is going to be equal to partial extended Hamiltonian with respect to minus e. And we apply this to this particular Hamiltonian constraint for a free particle moving in an inertial frame. And we end up getting that the change of time, the variable with respect to the affine parameter, is e over mc squared. For our QIs with respect to the affine parameter, this is partial extended Hamiltonian with respect to the PIs. I apply that to this and get PI over M. For DE, DS, this is partial extended Hamiltonian with respect to time the variable. This is 0, and my DPI, DS works out to be 0 as well. So I have E over C equals M dCT ds, and Pi equals M dQi ds. So we see that we have our 4 velocity here, and we see that ds that S is in fact proper time. So the Hamiltonian constraint is the generator for proper time. So you might see this S written as tau, or might be more familiar with it written as tau. We can compare this to the standard way. So working with the standard Hamiltonian, not in phase space extended by time. So the Hamiltonian for a free particle in an inertial frame would look like this with the square root. And then if we apply Hamilton's equations, again, not in the extended phase space, so just in standard formulation, then we get dqi dt is partial h partial pi. with the standard Hamiltonian, not extended in phase space, and it gets a bit messy with the square roots, and we end up having to take an absolute value. So it looks like this: pi over the square root of m squared plus pi squared over c squared. And okay, the dpi dt is still equal to 0. So if we compare this to what we got before, so our dqi dt, it was actually a lot easier to calculate and a little bit less messy and nice looking, in my opinion, and can show that these end up being equivalent. So E is the Hamiltonian and the standard Hamiltonian here. So you could plug this in and see that this is equivalent to this. So we think that Hamiltonian mechanics on the extended phase space comes out more naturally and is a nicer formulation. And the formulation, looking at the Hamiltonian constraint, it has a nice quadratic formulation. We have our p squared, e over c squared, m squared, c squared. So we've got a quadratic, so can E be negative? So when we write our Hamiltonian equations in phase space extended by time, remember we've separated time the variable from proper time, the affine parameter, and we had that dt ds is partial h with respect to minus e. And so this could be positive or negative. We can have our time the variable evolving with proper time in the same direction or opposite direction. So we get a classical analog of antiparticles. The particle case would have the affine parameter aligned with time. So like this, the antiparticle case would have the affine parameter anti-aligned with time. So the parameterization, right, this affine parameter that we called S, that's proper time, flows backwards with respect to time. And a note that any given evolution has to have either the forward parameterization or the backward parameterization. It can't change the sign of the parameterization in the middle. So an evolution cannot change time alignment. It has to be one or the other. And so for a free particle, you can look at this as an antiparticle corresponding to negative energy in the way we've written it here. So we can recover the standard Hamiltonian. So over valid states, physical states, we're going to have our Hamiltonian constraint equal to 0. And the energy E is going to be equal to the standard Hamiltonian, where time is just a variable, not, we don't have time, the affine parameters separated out. So we can write our extended Hamiltonian as some function lambda times h minus e. So h minus e for valid states is going to be 0. And so if we assume there's no e dependence and we have e equals h, then we get the lambda, or 1 over lambda, becomes the relationship between the affine parameter and time the variable. And we can write our Hamiltonian equations in the extended phase space in this way. I need to speed up a bit here. So note that the Hamiltonian constraint can actually hide multiple standard Hamiltonians. So if I have, go back a slide here, so I can write my Hamiltonian constraint as lambda h minus e. We said we had, again, this quadratic form of the free particle Hamiltonian constraint. So I can view this as h minus e and this as my lambda, or this as my h minus e and this is my lambda. And so basically I can have either a negative energy or a positive energy. So the Hamiltonian constraint can be written as h1 minus e or h2 minus e, and the solutions to make this 0, h1 or h2 are both equal to e, and h1 is going to be minus h2. So again, we see how negative energies can come out. So we can make a parallel to quantum mechanics here. So we can rewrite our free particle Hamiltonian constraint and compare this to the Klein-Gordon equation in quantum mechanics. And so I have, well, the m squared c squared term would correspond to this extra h bar here. We're not examining that in more detail now. The momentum term corresponds to the del squared here, and the e over c squared term corresponds to this time derivative here with the energy, or the traditional Hamiltonian being the generator of time. So already writing the Hamiltonian constraint for a free particle in classical Hamiltonian mechanics in the extended phase space, separating time the parameter and time the variable, we get something that looks very much like the Hamiltonian, like the Klein-Gordon equation in quantum mechanics. And if you look at the Klein-Gordon equation, we have our Hamiltonian, this part, the Hamiltonian equation, the Klein-Gordon equation is the Hamiltonian constraint, and then we have our state or our density. So the density can be non-zero, the state can be non-zero, only where our Hamiltonian constraint is satisfied. So looking at this for charged particles, we get something similar, again, just starting from classical mechanics on the extended phase space where we separate time the variable from time the parameter. And we have our gauge. So we have a charged particle now. We still have this you can think that this kinetic term, a pure 4-velocity kinetic term. We have this 1/2 mc squared term. But we can express our 4-velocity kinetic term in terms of the conjugate momentum and the vector potential minus the charge times the vector potential of the electromagnetic field. This whole expression is the kinetic momentum, so the momentum, which is physical. So the momentum gauge and the electromagnetic gauge must cancel out. We can compare this form when we recall that the 4-velocity kinetic term can be expressed in terms of this conjugate momentum minus q times the vector potential. We can now compare this to the electromagnetic Klein-Gordon equation in quantum mechanics, where we have our gauge covariant derivatives as the kinetic momentum, and we have this nice correspondence again. So takeaways from this section: relativistic mechanics is recovered without additional assumptions. Relativity is needed to make densities and entropies invariant over coordinate transformations that involve time, that mix space and time. Hamiltonian mechanics on the extended phase space is a more relativistic formulation, and the Hamiltonian constraint is the generator of the affine parameter, the generator of proper time. Yeah, it can be taken to generate proper time for particles and minus proper time for antiparticles, these classical antiparticles that come out. We also saw multiple connections to quantum mechanics when we treated classical Hamiltonian mechanics properly from a relativistic point of view, from handling time properly. Antiparticles are already present in classical Hamiltonian particle mechanics. You don't need quantum mechanics to have them come out. The Hamiltonian constraint is directly related to the Klein-Gordon, as well as the Dirac operators, and gauge considerations are already present in classical particle mechanics. So to summarize reverse physics for classical mechanics, all the core elements of classical mechanics can be rederived and understood using 4 physically meaningful assumptions: that of infinitesimal reducibility and degree of freedom independence. These 2 apply to all of classical mechanics. And then within classical mechanics, we may also we have some theories or some parts of classical mechanics where we are assuming determinism and reversibility and or kinematic equivalence. Again, that conjugate momentum there's a map, an invertible map that goes between conjugate momentum and velocities. So many physical ideas are a consequence of these 4 core assumptions. So the principle of stationary action, the massive particles under scalar and vector potential forces, which I didn't show in detail here, relativistic mechanics, and phase space, so conjugate quantities. And a great number of better insights. We were able to pull out a great number of better insights from a theory, classical mechanics, that's generally considered already well understood. And there's probably even more to be done. So let's now use the remaining time to look at why classical mechanics fails. So what is quantum mechanics actually fixing? If you look at the temperature entropy curve for ideal gases, we have entropy per particle as a function of temperature for Fermi and Bose gases, and then classical, where we have for the entropy per particle stopping at 0 for the Fermi and Bose quantum case. For classical, it's going down to minus infinity there. So this would be, so in classical mechanics, we have the entropy as the log of the count of states, or the log of the area in phase space. So for a single microstate, this is a mathematically infinitesimal point. This is perfectly allowed in classical mechanics. So the entropy of your single microstate would be the logarithm of zero, zero area of a point. So we have minus infinity. Now, classical physics allows arbitrarily small entropy, but thermodynamics does not. So the third law of thermodynamics says that the entropy has to be greater than or equal to zero. And there are a lot of different formulations of this. This one from a 1923 textbook says every substance has a finite positive entropy, but at the absolute zero of temperature, the entropy may become zero and does so become in the case of perfect crystalline substances. Again, we think sounds very specific. We think there are better formulations of this as well that reverse physics can come up with. So looking at we saw in the last lecture, the classical uncertainty principle. First, we fixed this expression, entropy, as minus rho log rho, dq dp, integrated over an area in phase space. So we saw that writing rho log rho, where rho is phase space density. So we're taking a logarithm of something with dimension that's not dimensionless. We had to fix this by inserting a constant that has dimensions of phase space area or phase space volume, depending on what the number of dimensions you're in. And so to make this zero, we saw that the uniform distribution over phase space area of our constant h is the one that has zero entropy. So if it's a uniform distribution over area h, then rho would be just 1 divided by h. So h times 1 divided by h is 1. Logarithm of 1 equals 0. So we get 0 entropy over a uniform distribution over phase space area h. And we saw that in general, Gaussians maximize entropy for a given uncertainty. So we can start from here, put a Gaussian distribution in, and say that the entropy must be less than or equal to the logarithm of 2 pi e times sigma q sigma p divided by our constant that fixed the units. And then we can algebraically rearrange this expression and exponentiate both sides to say that sigma q sigma p must be greater than or equal to our constant h divided by 2 pi e times e times the exponential of the entropy. And if we write h over 2 pi as h bar, then we get this classical uncertainty principle. So sigma q sigma p equals minus h bar over e times our lower bound on entropy, or times whatever our entropy, the exponential of whatever the entropy is. So entropy puts a lower bound on the uncertainty, and thermodynamics puts a lower bound on the entropy. So the entropy, requiring the entropy to be greater than or equal to 0 means that you have sigma q sigma p greater than or equal to h bar over e in classical, coming from classical mechanics, adding the assumption of the third law of thermodynamics. We have no quantum mechanics yet. So if we compare the two theories, in classical mechanics, we have this classical uncertainty principle must be greater than or equal to h bar over e. So e is about 2.718. Quantum mechanics, we have our uncertainty principle, sigma q sigma p must be greater than or equal to h bar over 2. The entropy of quantum states is already non-negative, so the entropy of pure states in quantum mechanics is 0. So quantum mechanics as a theory has it built in that 0 is the minimum entropy possible. You can't go to negative entropy. And then the Gaussian bound, that in classical or quantum mechanics, the maximum entropy for a given uncertainty is for a Gaussian distribution. So this area would be excluded by the Gaussian bound. This area is excluded by the third law of thermodynamics. And if we plot entropy versus uncertainty in units of h bar, we see that already for a few units, so here we can see that the blue curve is the classical one crossing 0 at h bar over e. The red dashed curve is the quantum one crossing at h bar over 2. So we can see there's a difference here, but already at a few units of h bar, uncertainty a few units of h bar, we get very little difference. I mean, we can't, on the scales here, you can't even see the difference. At 2 units of h-bar uncertainty, the quantum and classical curves coincide. So quantum mechanics incorporates the third law and classical mechanics does not. Is this the only difference between the two theories? So suppose the lower bound on the entropy is the only difference between classical and quantum mechanics, then in the limit of high entropy of quantum mechanics, we should be able to recover classical mechanics. So can we do this? And so Gabriel, back in June 2024, posted an open problem on the research channel on YouTube, laying out these ideas and saying what we had so far and what we couldn't get things all the way there. Within 6 weeks or so, in mid-July, a researcher, Manuele Landini, working in Austria, reached out after seeing the video. And by the end of 2024, we had a submitted paper recovering classical mechanics as a high entropy limit of quantum mechanics. As I said at the end of the previous lecture, Assumptions of Physics is an open research program. And we have open problems posted on the website. Gabriel makes videos on some of them. We welcome contributions from people who have relevant knowledge and expertise. So we were, not familiar with this researcher or his work prior to his seeing the video and reaching out to us. So we're looking for a map that increases the entropy of all mixed states such that every level set of entropy maps to another level set. So we have entropy versus uncertainty in units of h-bar, again, the same basic figure. So for a given entropy is the vertical axis. So for a given entropy, we want to find a map that increases the entropy of all mixed states uniformly. So a unitary transformation then must be mapped to other unitary transformations in the limit that we take the entropy to infinity. So we have this stretching map. We take the commutator xp equals I(h)bar to this mapped or stretched x and p, such that we rescale the commutator by this lambda. So we work with an open quantum system to increase the entropy of mixed states. Another perspective is to look at this not as increasing the entropy of the mixed states to infinity, but instead to move the entropy of the pure states from 0 down to minus infinity. So instead of rescaling the commutator to scale things up, we can redefine the original space such that our commutator in the original variables is I(h)bar divided by this parameter lambda. So that when we take lambda to infinity, h-bar over lambda goes to 0. So the commutator would go to 0. So this is the perspective of moving the pure states to minus infinite entropy. This is a mathematical perspective rather than a physical perspective. This is mathematically equivalent to lowering the entropy of a pure state to minus infinity, or h-bar goes to 0, like a group contraction, analogous to taking the mathematical limit of c goes to infinity to recover, as a mathematical way to recover non-relativistic mechanics from relativistic mechanics. And again, you can see that with scale factors, so here's our quantum distribution, the dashed red line. The solid blue line is the classical curve that goes down to minus infinity. If we scale, use this formulation of it, redefining our original space, and then have the commutator rescaled by 1 over this lambda. Already for lambda equals 2 is this green dashed line. Lambda equals 10 gives us this purple dashed line. You can see that things already coincide very nicely with the classical limit, or the classical curve for scaling variable values of just a few. So we think that the physical way of looking at quantum mechanics going to classical mechanics is to look at the high entropy limit as opposed to the mathematical but completely unphysical limit that you often see in textbooks. H-bar goes to 0, H-bar doesn't go anywhere, it's a constant of nature. just the way that we look at relativistic, or going from relativistic to classical mechanics as the v over c much less than 1, and mathematically you could view this again as an unphysical mathematical limit taking the speed of light to infinity. And it's a no mechanism limit, right? So it doesn't matter how your entropy is increased. People talk about decoherence, you have interactions with the environment, whatever is going on. It doesn't matter how your entropy increases, you're going to get classical behavior at high entropies, just like it doesn't matter what going from relativistic to non-relativistic classical mechanics, it doesn't matter what is leading to velocities small or speeds small compared to the speed of light. You get classical mechanics no matter what. So in quantum mechanics, people seem to want to look for mechanisms to recover classical mechanics in a way that nobody is looking for mechanisms that reduce the speed of things to make them behave classically. So anything that gives you high entropy will give you a classical limit. So Dirac's, if we look at Dirac's correspondence principle relating the Poisson bracket in classical mechanics to the commutator in quantum mechanics, what we should be thinking of it in terms of is a theory with an entropic lower bound that recovers the classical one at high entropy. And mathematically, we see that there's only one way to do this. So the Moyal bracket, for those who might be familiar with it, is the unique one-parameter Lie algebraic deformation of the Poisson bracket that is used in classical mechanics. So ultimately, the physical perspective is that quantizing a classical theory means putting a lower bound on the entropy. And as we saw in the first lecture, geometry is equivalent to entropy in our different physical theories. So the geometric structures of both classical and quantum mechanics are equivalent to the entropic structures. So in classical mechanics, we have our symplectic manifold, and we have standard probabilities and information theory that relate, so this geometry relating to entropic structures and probabilities. And then in quantum mechanics, we have the Born rule and projective Hilbert space, and we have our quantum probabilities and entropies and quantum information theory. We shouldn't think of thermodynamics and statistical mechanics as being built on top of mechanics. We think a more intuitive way to think about the relationship between mechanics and thermodynamics or statistical mechanics is that mechanics is the ideal case of thermodynamics and statistical mechanics. So reverse physics, summing up here, reverse physics tells us that there are not many independent concepts in our physical theories. So extracting different principles and assumptions behind the laws of physics in different theories gives us solid intuition that cuts across different fields and leads to new insights and results. But the only way to be sure that we got all the concepts is to derive all the math from scratch, which leads us to physical mathematics, which will be the topic of tomorrow's lectures. So again, I just want to reiterate, Assumptions of Physics is an open research program. You can find all sorts of materials on our website and on Gabriel's YouTube channels. And if you'd like to get more involved, feel free to contact us to join our Discord server. All right, that brings me to the end of lecture 2.
There you go. Thank you, Christine. And as usual, we open for questions. No question yet. If anybody's following from YouTube, I'm also monitoring the YouTube chat in case that somebody wants to post questions from there. Question from Zoe. Could you elaborate how reverse physics changed the way we look at the results you covered in this lecture?
Reverse physics changed the way we look at the results covered in this lecture. So we covered the action principle, the principle of stationary action. So we have the principle of stationary action is typically formulated just purely mathematically, that the variation of the action is required to be zero. So we saw using reverse physics approaches that it's really encoding the fact that you're requiring deterministic and reversible evolution of states in time. So you have classical states, so states in phase space that are evolving in time, and you are imposing deterministic and reversible evolution. And a way to do this mathematically is through requiring the variation of the action to be zero. So really, yeah, that's if we saw that as the physical content of the principle of least action. For relativistic mechanics, we saw that some things typically associated with quantum mechanics or even quantum field theory come out already from treating classical Hamiltonian mechanics properly with respect to coordinate transformations that involve time, so where that might mix time and space coordinates. And so if you do, I don't think that we did find some literature, but none of the standard textbooks on classical mechanics that I'm familiar with as being widely used have this formulation of classical Hamiltonian mechanics on the extended phase space that separates time the variable from the affine parameter. So we saw how we got already a notion of antiparticles as states that evolve where the parameterization is anti-aligned with time and the variable and particles. So nothing related to quantum mechanics or quantum field theory there. It was really just relativistic classical Hamiltonian mechanics. And we saw how the Hamiltonian constraint for classical Hamiltonian mechanics on this extended phase space, separating time the variable from time the parameter, also has this direct correspondence to the Klein-Gordon equation going to quantum field theory. And what else? We saw how the uncertainty principle in quantum mechanics doesn't come from any features of quantum mechanics except the lower bound on the entropy. So as soon as you impose a lower bound on the entropy, you necessarily get an uncertainty principle. So I'm not sure if that was the answer, the type of answer you were looking for, but hopefully the idea is to see what's in the mathematics and see what physical assumptions are leading to different mathematical results to get much better intuition about the physics that's encoded implicitly in the different theories that we use.
Okay. We can go to the next one. In the section of relativistic mechanics, if you assume time and the affine parameters are neither aligned or anti-aligned, but have a kind of phase difference between them similar to anion in quantum systems, what kind of physics would it lead to in the context of relativity?
So the aligned or anti-aligned, you can have a constant. It's not that it's a 1 or -1. You can have different constants with respect to t relative to s, as we called it. But I guess you're talking about a different constant between the parameterizations in one direction or the other direction, which I have not thought about,
the
which would not
parameterization
come out in what we did, right? We can't get a
right. So
yeah.
both for the affine parameter and time are real parameters, and the derivative between them cannot be zero. Like that's the thing, because at every time you have one and only one value of the affine parameters, and from every value of the affine parameters you have only one and one time instant. So the relationship between time and the affine parameter has to be strictly monotonic. And it can be increasingly monotonic in the case of the particle, and decreasingly monotonic in the case of the antiparticle. So those are the only two cases. The function between the two can be arbitrarily complicated. It does not matter. So it is a constant only in in the parameters that we chose for a free particle. In that case, it's all nice and it's a constant, but you could choose a different reference system where time is a lot more complicated, and you wouldn't have like just a nice constant. You would have a function.
But I don't think the question was about whether it can be, or the fact that it can't be zero, and therefore it has to be either have a positive or negative derivative. I think it's that you would have a different function for the aligned and anti-aligned cases relating T and S, which from what we did you can't get. I mean, you solve for any given Hamiltonian constraint, you're going to solve it, and maybe you get some complicated function, but it's still going to be the same function with the plus or minus sign, right? You can't get different functions.
No, but okay, the question says the affine parameters are neither aligned or anti-aligned.
Right, but
those are the only two cases possible. There is no other case.
right, but then the question is about having a phase difference between the aligned case and the anti-aligned case. I don't know if it'd be called a phase, but I'm interpreting that as different functional forms. So you have a plus one function and minus a different function for the aligned and anti-aligned cases, which would not come out with what we went through.
Yeah, it's not that it wouldn't come out. You just
Can't.
so you're gonna have a foliation based on the affine parameter, right? So you start at affine parameter equals 0. You have all the initial condition, and then you increase the affine parameter. You're gonna foliate all of the extended phase space, and yes, that foliation can do weird things, but it's still one foliation. So you always have the same type of relationship, that there is nothing strange that can happen. Like in the context of quantum mechanics, you'd have a problem that you might have, can I say, interference patterns and so on, because when you're evolving the wave function, things are going to get more complicated. But here you're evolving point to point, so that there isn't anything that can happen. Next question. I know it's tangential, but in the relativistic Hamiltonian script H, how was that derived in a nutshell? Just a relativity view also has the progress, what has the progress been made in statistical mechanics? Okay, for the Hamiltonian constraint, it's basically, I can say, it comes out when you are generalizing your your non-relativistic, like the standard case, because energy itself does not add, so the time energy do not add any new states, right? The only thing that you have is that the states are mapped back and forward in time. And so when you're adding your time energy degree of freedom, the temporal degree of freedom, you now have in case of 3 degree of freedom, you have an 8-dimensional space, but the space of states is still 6-dimensional, and the time is just moving those states back and forth. So you need something else to recover the fact that you only have a 7-dimensional manifold. That other direction is it doesn't give you new physics. And so the Hamiltonian constraint gives you that. Basically, you are on an 8-dimensional manifold, you put your Hamiltonian constraint, and now you have a 7-dimensional manifold, which is the correct one. The thing that is interesting for the particle-antiparticle is that constraint can essentially can give you 2 disconnected parts of phase space, which you didn't have before, right? That's the new thing that the frameworks allows you to do. And for progress in statistical mechanics, so essentially, I'm gonna say, a lot of the stuff that we do are automatically relative statistical mechanics, because we are already thinking about entropy probability distribution. So whenever we have a condition, it's can be expressed as the motion of points, but it can also be expressed as motion of a statistical distribution. So in the context of statistical mechanics, in the sense as evolution of probability distribution under mechanics, that we already have. What we don't have, it's the typical max ent type of calculation that one does in statistical mechanics. You fix a Hamiltonian, you maximize the entropy, you find the Boltzmann distribution, all that. We don't have it in the sense we haven't found a good physical justification for that yet, but we haven't looked that hard, and we already have some ideas of how that would work. But it's something that we still need to work to have the final results, let's say. Okay, next one. I have to ask somebody about the notes as I have not understood. Oh, all the slides will be posted on our website this evening. I will go and start making the page. We did that for the same for the summer schools for the previous year, so all of that is going to be available on our website. And then, how would you consider the Hamiltonian constraint as useful in showing how velocity-based time dilations occur?
You want to answer that one?
I don't
think.
have.
Okay, so I don't have a ready answer.
I don't have a ready answer for that. Trying to think if I can think about one off the top of my head. It's probably very unlikely. At the end of the day, the Hamiltonian constraint, if you look at it, is just telling you that the norm of the forward velocity is equal to c. That's basically what for a free particle at least. That's the only thing that it's telling you. So I assume that you can directly think about time dilation and all that, because at that point you're basically making a booster and then seeing how I don't have a good idea. I don't know if any of you can, but the Hamiltonian constraint in the free particle case is just telling you that the norm of the forward velocity is c. Which is interesting because, as we saw, the Hamiltonian constraint for the free particle is the Klein-Gordon equation. So while the Klein-Gordon equation might look complicated, it's still telling you, and just telling you, the norm of the forward velocity is c, and it's not telling you anything else. So this is, going back to the question from before, like how does doing reverse physics kind of change perspective? It's kind of that, like instead of like looking at this complicated mathematical relationship, you can basically say, oh, this complicated math is just telling me this one thing, which is simple, and only that thing. And in principle, you should be able to then make, everything that you can derive from the equation, you should be able to get from that simple idea. But, creating the simple argument and steps from just that simple idea might not be so simple. So we don't have all of those yet, but there is probably space to create this, which might help get more physical intuition and also teach this stuff better. Any other questions?
Can comment briefly about teaching this stuff better. So, okay, well, all right, I'll make a brief comment. Yeah, we think a lot of things can be taught a lot better from a much more physical point of view. So we're not rewriting textbooks yet, so to speak. But if there are people interested in helping us create materials aimed at classes, we would welcome that. Another question now.
I'm not sure whether this question is fully relevant to the framework developed in the book, but I was wondering about the role of dissipative and open systems in the context of classical mechanics. And many of the derivations seem to rely on deterministic and reversible devolution, which ultimately leads to a Hamiltonian flow and phase space volume preservation. However, in engineering, we often deal with systems subject to friction. In fact, everything is subject to friction. Viscous damping, external forcing, control inputs, and energy exchange with the environment. My question has two parts. For the system that exhibits dissipation or are driven by external inputs, are there generally
And therefore,
and therefore generally produce phase-space contraction that are not time reversible? Which of the fundamental assumptions of the framework should be regarded as failing? It is reversibility itself, a determinist, infinitesimal reducibility, or something else?
so it's going to be the infinitesimal reducibility and independence of degrees of freedom are the two assumptions relevant for all of classical mechanics. And then determinism and reversibility is an additional assumption that would apply in some cases and not to others. So if you assume it, then you get classical Hamiltonian evolution. If you don't assume it, you don't get classical Hamiltonian evolution. And within Newtonian mechanics, you certainly can handle driven and dissipative systems. So we're actually, after we published our paper on geometric and physical interpretation of the principle of least action, an applied mathematician in Hungary reached out to us about extending it to dissipative systems. So that's actually something we're working on right now. So it's a generalized, so it's going to be, of course, different from the principle of least action, because the principle of least action, as we demonstrated, has implicit in it the assumption of deterministic and reversible time evolution. But we're trying to develop a generalized principle of least action, if you will, that will look different and be relevant for driven and dissipative systems.
I'll get the second part and then I'll comment after you finish the second. Should such system be viewed as a genuine violation of the assumptions underlying Hamiltonian mechanics, or rather as indication that the state description is incomplete and must be enlarged to include the environment or other external degrees of freedom so that reversibility is recovered in a higher dimensional state space?
So we would view them as dissipative or driven systems as violating the assumptions underlying Hamiltonian mechanics. So it's just, so a lot of reverse physics is about understanding the physical assumptions in our different physical theories and understanding the limits of applicability. So we would just say you shouldn't be applying, if you're doing things wrong. If you're assuming deterministic and reversible evolution by using Hamilton's equations, and you have a system that is dissipative or driven, so it's not deterministic and reversible, then you're using the wrong theory to try to describe the physical system of interest to you. So it's not that it's not a violation in the sense of like, oh no, something went wrong. It's really that it's not the relevant theory to apply to problems with dissipative or driven systems.
Yes.
Yeah.
To extend more of that, one of the problem that happens when you fail a deterministic and reversible evolution is that the independence of the degree of freedom might not be conserved by the system. So you could imagine, in fact, that you have a system that starts as 2 degrees of freedom, and then it goes completely dissipative in one direction, and it contracts to 1 degree of freedom, right? At that point, the number of degrees of freedom is effectively changed, and these things can happen when you have friction. So the bigger issue is how can you even define an entropy when such things are happening, and is there a unique way to do it or not? And entropy also means count of state, proper density of probability distribution, and so on. Because one of the things that you can imagine, for example, let's say that we have a damped harmonic oscillator, right? So if I have a damped harmonic oscillator, the trajectory in phase space are going to spiral up and go and tend to the origin. Now, this is something, if you look at the areas of phase space, areas of phase space are shrinking. And if you think about entropy, right, the entropy is decreasing. But it's an irreversible system, so you might want to say that the entropy is increasing. But you could also look this in a completely different way and say, if I told you some information about the initial state, let's say that I'm in this disk, right? That information is the same after the evolution at time t that the system is in a smaller disk. So you might, instead of saying, oh, my distribution is decreasing entropy, you might be able to say that areas in phase space at different time correspond to different amount of information and therefore different entropy. Which is the correct way of looking at this? And if it's there is one correct way of looking at this, to me, is completely unclear. And again, last week I was looking at people doing statistical mechanics that have similar problem because they say, okay, I'm out of equilibrium and I have a system and environments and I've coupled and they're coupled and the coupling is not negligible. How do I split the system? It's completely unclear how to do it. There are people that are proposing different ways, and everybody, of course, thinks that they have the right way to do it, and it's the same problem. So even if you say, I see the whole system and I want to split it into two, or I just say I have one system that it's either driven or dissipative or both, you still have the same problem because you do not know exactly how to split things. And that seems to be like an open research area. And again, it's one of those cases where spelling out the assumption that are underneath all of this and what is that engineeristically you're interested in. Because again, you develop a model because in some particular condition you're interested in doing some things. So maybe even depending on what are your work variable that you're using to control the system or to take energy out or put heat in, maybe that is going to tell you, oh, you want to partition the system in different way, because at the end of the day, for you, the system is the part that you can control and manipulate, and depending of how you're controlling and manipulating, you might be defining the same physical object as a different physical system. So all these questions are completely open. They are absolutely interesting, and again, the way that we're trying to solve all these things is first to sort of have a complete mathematically and conceptual crisp way to look at the simple cases. And then we are going to be able to say, okay, if we fail this assumption, what is it that we can do? Because now we have a pattern of knowing how to use these assumptions precisely, which is the problem that we have in physics right now. We don't have a pattern of how to do the modeling in a precise way. And so everybody says, oh, I'll do this. And we don't understand exactly what are the limitations of all these models. So I hope that answers the question. I'll wait another 60 seconds in case there are people that are typing. And if there are no questions, we can close. Okay, I think we have emptied all the queues, so we should be able to stop for today. Thank you everybody for following, both here on Zoom and on YouTube, and we'll reconvene tomorrow. Bye.
Right?